We are on a crash course with our adjoining huge universe, Andromeda, an arrangement of a few hundred billion stars. This crash will prompt a common plunge, adjusting the two systems in huge ways. The Andromeda world, generally essential in showing that the universe didn't rotate around us, has been the focal point of galactic review for north of a century. It was Andromeda that demonstrated the Milky Way was not by any means the only universe, changing our understanding of the cosmos. While much has been gained from Earth advancements like the James Webb Space Telescope, which have given new stunning insights about Andromeda that we didn't predict for a whole 100 years, our comprehension of the universe has evolved. A little more than quite a while back, the Milky Way was seen as a weak band of light across the night sky due to restricted technology that forestalled the insight of individual stars. Different convictions about the Milky Way focused it in creation. This changed in the early 17th century when Galileo Galilei utilized his telescope to see that the Milky Way was not just a band of light but a tremendous assortment of stars, planets, and divine objects. Galileo's work exposed the idea that the Milky Way was the focal point of the universe, revealing it as a sprawling breadth of stars. In 1750, English astronomer Thomas Wright speculated that the Milky Way was a flat layer of stars, including our solar system, a hypothesis limited by the technology of his time. By the early 1900s, significant progress was made in cosmology. During the 1920s, Edwin Hubble utilized the Hooker telescope at Mount Wilson Observatory to demonstrate that far-off nebulae, including the Andromeda system, were discrete universes with billions of stars. This fundamentally changed our understanding of the universe. The Andromeda world, also known as M31, has been observed since at least the 10th century, when Persian astronomer Abd al-Rahman al-Sufi described it as a little cloud. Al-Sufi's keen visual perception allowed him to distinguish Andromeda without adjustable instruments, an accomplishment made possible because Andromeda is one of the few systems visible from Earth's surface without special instruments. It wasn't until 1612 that Simon Marius provided an adaptive description, laying the groundwork for future cosmologists. In 1764, Charles Messier catalogued Andromeda as M31, encouraging its acknowledgement. A significant leap in understanding Andromeda occurred in 1864 when English astronomer William Huggins studied its spectrum, finding it different from normal gaseous nebulae, which was a crucial observation. Andromeda is enormous, with a mass estimated to be between 1 and 2 trillion times that of our Sun, and is believed to be around 10 billion years old, suggesting a complex history of development through the merging of smaller protogalaxies. Previously, cosmologists thought Andromeda was substantially more gigantic than the Milky Way. Later research has amended these estimates, showing that the two systems are much closer than previously suspected. Expectedly, Andromeda's actual dimensions are larger than the Milky Way's, with a diameter of around 220,000 light-years compared to the Milky Way's 100,000 to 175,000 light-years, highlighting its vastness. One of Andromeda's interesting features is its dynamic cosmic core, fueled by a very gigantic black hole with a mass between 110 to 230 million times that of our Sun. Observations utilizing advanced telescopes like the Hubble Space Telescope show two places of concentration in the Andromeda world, with the brighter one slightly off the true cosmic center, indicating intense gravitational interactions and the presence of a very massive black hole. Andromeda also has an abundance of globular clusters, estimated at around 460, each containing many thousands to millions of stars. This abundance demonstrates Andromeda's history of cosmic violence, where smaller systems were absorbed into Andromeda, adding to its stellar population and diversity. Observations suggest that Andromeda might be transitioning from a spiral galaxy to a ring galaxy, a relatively rare type characterized by circular ring-like structures of bright young stars. Ring galaxies can form through cosmic collisions or when a smaller galaxy passes through the center of a larger one, making them intriguing among cosmic structures. The impending collision between the Milky Way and the Andromeda world is a grandiose event anticipated to begin around 4 billion years from now and will unfold over the subsequent 2 billion years. This grand event will culminate in the formation of a new supergalaxy, nicknamed Mila by cosmologists and enthusiasts. The merging process will be characterized by significant gravitational interactions and tidal forces, greatly affecting both galaxies. As the Milky Way and Andromeda approach each other, their immense gravitational forces will begin to distort each other's shapes. This gravitational interaction will pull stars, gas, and dust from each galaxy, creating elongated tidal tails and triggering a series of complex gravitational interactions. The crossover and blending of the two galaxies will not be a smooth process. Rather, it will be marked by turbulent and dynamic changes as their structures are gradually disrupted and transformed. One of the most dramatic results of this collision will be the formation of new star clusters. As the galaxies merge, the gas clouds within them will collide and compress, leading to bursts of star formation. These stellar nurseries will be regions where intense gravitational forces compress the gas to the point of collapse, forming new stars. These newly formed stars will often group together into clusters, advancing the new supergalaxy with new stellar populations. Simultaneously, the gravitational upheaval will cause changes in the orbits of existing stars. Stars previously in stable orbits around the center of the Milky Way or Andromeda will be thrown into new, more elliptical orbits or possibly ejected from the merging system entirely. Some stars may end up catapulted into intergalactic space, becoming rogue stars no longer bound to any galaxy. This reallocation of stellar material will contribute to the development of new galactic structures and may result in a complex web of star streams and clusters that blend the remnants of both galaxies while also forming new stars and clusters. The merging process will also create large-scale structures within the new galaxy. The gas, dust, and cosmic debris from both galaxies will mix and settle into new configurations, forming vast regions of star formation, twisting arms, and potentially new galactic features that are a hybrid of both the Milky Way's and Andromeda's original structures. These structures will evolve over time, influenced by the new dynamics of the merged galaxy. The very massive black holes at the centers of the Milky Way and Andromeda will also play a crucial role in the merger. As the galaxies coalesce, their central black holes will eventually merge, forming a single, even larger supermassive black hole at the center of Mila. This merged black hole will be a powerful source of energy and will significantly influence the surrounding cosmic environment, contributing to the new galaxy's dynamics and advancing features. Ultimately, the consolidation between the Milky Way and Andromeda will result in a completely transformed astronomical scene. The new supergalaxy, Mila, will be a colossal entity made from the combined material of both precursor galaxies. It will feature a rich tapestry of new star clusters, reorganized stellar orbits, and reconstructed galactic structures. This process of cosmic evolution, driven by the collision and merger, will shape the fate of the local group of galaxies and provide a fascinating glimpse into the long-term dynamics of cosmic interactions. The merger will result in significant changes to our night sky and the environment on Earth, potentially influencing climates, biodiversity, and ecosystems. However, this process will occur long after humanity is gone, as our sun will evolve into a red giant and render our solar system uninhabitable in about 5 billion years. The merger of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new galactic structures. The cosmic interactions will shape a new galactic environment, potentially with habitable zones for potential life forms, although vastly different from what we know today. The Mila galaxy will be a testament to the dynamic and ever-changing nature of the universe. The crash between the Milky Way and Andromeda, anticipated to happen in around 4 billion years, will be a spectacle of cosmic proportions. It marks the end of a gravitational dance that began billions of years ago, when these two massive galaxies first started their inevitable approach toward one another in the vast expanse of space. As the merger progresses, one of the key phenomena astronomers expect is the transformation of both galaxy spiral structures. Currently, the Milky Way and Andromeda are spiral galaxies, characterized by their distinctive arms extending outward from a central bulge. These spirals are defined by the rotation of stars and gas around a central core, creating visible structures observable from Earth. However, as the galaxies move ever closer, gravitational effects will interlace these spiral patterns, causing massive changes. The mutual gravitational attraction between the Milky Way and Andromeda will warp their shapes, stretching and elongating their spiral arms into extended tidal features. These tidal tails will be composed of stars, gas, and dust that have been pulled away from their original galactic orbits, creating a turbulent yet mesmerizing display across the cosmic landscape. The collision will also trigger intense bursts of star formation within the newly forming supergalaxy. The interaction of gas clouds from both galaxies will compress and heat up, leading to the creation of massive, luminous star clusters. These clusters will become nurseries for young stars, whose bright radiation will illuminate the surrounding cosmic dust and gas, giving rise to new stellar populations. The merging process will not only affect the appearance of the galaxies but also their internal dynamics. The gravitational interactions among stars and gas clouds will cause a reshuffling of their orbits and velocities. Some stars will be flung into more eccentric orbits, while others may be ejected from the merging system altogether, becoming free-floating rogue stars in the intergalactic void. Meanwhile, the supermassive black holes at the centers of the Milky Way and Andromeda will play a crucial role in shaping the future of the merged galaxy. These behemoths, each many millions of times more massive than our Sun, will eventually spiral toward one another, influenced by gravitational waves emitted as they orbit closer together. The final stages of black hole merging will be catastrophic, releasing enormous amounts of energy into space in the form of gravitational waves and radiation. This merging event will create a single, much larger supermassive black hole at the core of the newly formed galaxy, surrounded by a swirling accretion disk of gas and dust. The presence of such a powerful central engine will have significant implications for the evolution of the supergalaxy, driving the formation of stars and influencing the dynamics of gas and dust within the galactic center, potentially triggering quasar-like phenomena as material falls into the black hole and emits intense radiation across the electromagnetic spectrum. On a larger scale, the merger of the Milky Way and Andromeda will contribute to the ongoing development of galactic structures in the universe. Galaxy mergers and interactions are crucial processes in the hierarchical model of galaxy formation, where smaller structures combine to form larger and more complex systems over cosmic timescales. Studying cosmic collisions like the one between the Milky Way and Andromeda provides astronomers with insights into the processes driving galaxy formation and evolution. By observing how stars, gas, and black holes interact during such events, scientists can test theoretical models of galaxy mergers and refine our understanding of the underlying processes. The merger will also have implications for the distribution of dark matter within the newly formed supergalaxy. Dark matter, an invisible and elusive form of matter that makes up a significant portion of the universe's mass, plays a crucial role in shaping the structure of galaxies and their gravitational interactions. During the merger, the gravitational forces exerted by the dark matter halos surrounding the Milky Way and Andromeda will interact and combine, impacting the overall distribution of dark matter in the new galaxy. Observing the effects of dark matter during and after the merger will provide valuable insights into its nature and properties, helping astronomers unravel one of the greatest mysteries of modern cosmology. The merger between the Milky Way and Andromeda will also offer a unique opportunity to study the formation of galaxy groups and superclusters. These enormous cosmic structures, made up of multiple galaxies bound together by gravity, are the largest known structures in the universe and provide insights into the large-scale distribution of matter and the formation of cosmic web-like structures. As the Milky Way and Andromeda merge, they will bring their respective satellite galaxies along for the ride. These smaller galaxies orbiting around their larger counterparts will be gravitationally incorporated into the merging process, either merging with the new supergalaxy or being disrupted and assimilated into its extended halo of stars and gas. The fate of these satellite galaxies will depend on their orbits and velocities relative to the merging Milky Way-Andromeda system. Some may survive the merger relatively intact, becoming dwarf galaxies within the new supergalaxy, while others may be disrupted and eventually absorbed into the larger structure. The merger between the Milky Way and Andromeda will also have implications for the cosmic environment surrounding our solar system.